Hello everyone, welcome to Enviro Pioneers. In this video, we will learn the concept of lapse rate and will understand the difference between environmental lapse rate and adiabatic lapse rate. As we saw in the previous videos that the temperature it changes in different layers of the atmosphere as we move from the earth surface to high in the altitude. It decreases in the troposphere, increases in stratosphere, again decreases in mesosphere and then increases in thermosphere. So this rate of change in temperature which is observed while we move upward through the earth's atmosphere, this is defined as the lapse rate. So, this lapse rate is simply the rate of change in temperature with height. As this lapse rate is very important in predicting the atmospheric stability, cloud formation. So, we have another definition of the lapse rate which is defined with respect to the troposphere, where the lapse rate is defined as the rate at which temperature decreases with height in the atmosphere. So here we have the formula for the lapse rate. L is equal to minus dt by dz. This minus it shows the decrease of temperature with height, and dt, that is the change in temperature, and this dz, that is the change in altitude. For example, if the temperature at 0 feet means here it is 85 degree Fahrenheit, and the temperature at 1000 feet is 80 degree Fahrenheit. So, if we calculate the change in temperature, that is 85 minus 80, 5 degree Fahrenheit, and the change in altitude is 1000 minus 0 feet. So, here we have 1000 feet. So, if we calculate the lapse rate, that is simply dt by dz. So, that will be 5 degree Fahrenheit by 1000 feet. As per this definition of the lapse rate is considered positive when the temperature decreases with elevation. It is 0 when the temperature is constant with elevation, and it is negative when the temperature increases with elevation. So this temperature increase with elevation, it is referred as the temperature inversion. This we will cover in detail in one of our upcoming videos. The International Civil Aviation Organization it defines an international standard atmosphere with a temperature lapse rate of 6.5 degrees Celsius per kilometer from sea level to 11 kilometer. Now this international standard atmosphere it is a static atmospheric model of how the pressure, temperature, density, and the viscosity of the Earth's atmosphere change over a wide range of altitude or elevation. So here you can see it is mentioned as an average. So this value, it is the average value of the lapse rate. And another important thing to notice, it is static atmospheric model. Means we are not considering any sort of disturbance or any vertical movement of the air. And from 11 kilometer to 20 kilometer, as we saw, the temperature is constant. So this constant temperature is minus 56.5 degrees Celsius, and this standard atmosphere for which this lapse rate is calculated, here it is considered that it is not containing any moisture. So this 6.5 degrees Celsius per kilometer value of the lapse rate for a static atmosphere, it is known as the environmental lapse rate. This environmental lapse rate is also known as the normal lapse rate, and it defines the lapse rate of the non-rising air, and it is the actual rate of decrease of temperature with altitude in the troposphere at a given time and location. And this environmental lapse rate it is highly variable because it is affected by the radiation, convection, and condensation. And the average value of the environmental lapse rate it is 6.5 degrees Celsius per kilometer in the troposphere. And as this environmental lapse rate is highly variable, it must be regularly measured. And for this, we use the radio sondes, which measure the actual environmental lapse rate along with the information about the vertical changes in the air pressure, wind, and the humidity. This radio sonde is an instrument package that is attached to a balloon, and it transmit the data by radio signal as it ascend through the atmosphere. मीन्स जैसे जैसे ये हाइट में ऊपर की तरफ जाएगा, जो भी डेटा इसने रिकॉर्ड किया, it will be sent to the base station through the radio signal. Environmental lapse rate is also affected by the temperature inversion condition. So, this is the normal condition where we have the warm air near to the ground, and as we move up, we have the cooler air and then cold air. But in the temperature inversion condition, we have a shallow layer where the temperature actually increases with height. So, we can see here we have the cooler air, but in between these two, we have a layer of warm air. So this reversal condition where the temperature increases with height, it is also affecting the environmental lapse rate. As our atmosphere, it is largely transparent to solar radiation but are more absorptive of the terrestrial radiation. So the atmosphere, it is heated from the ground up, and this heating, it may be because of the conduction, convection, or the radiation. As we can see, air pressure and air density both decrease with increase in the altitude. Near the ground, we have the high air density, means more number of molecules per unit volume. More the number of molecules means more heat and high temperature. But as we move up in the altitude, air density decreases, means there are less number of molecules per unit volume, and also they are scattered from each other. So as we move up in the altitude, we find a general drop in temperature. So farther from the radiator, means from the earth surface, the colder is the temperature of the atmosphere. The environmental lapse rate, it can vary over the course of day as a result of fluctuation in weather, or it can vary seasonally and also from place to place. To understand this, let us consider an example. Suppose if we have the data of temperature at 1000 meter, 2000 meter, 3000 meter from radio sound instrument, and the data are at 1000 meter it is 18.5 degrees Celsius, at 2000 meter it is 12 degrees Celsius, and at 3000 meter it is 5.5 degrees Celsius. And if we calculate this lapse rate, it is 6.5 degrees Celsius per kilometer. Now we are considering three hypothetical conditions, and here we are having the temperature of the atmosphere at three places at 0 meter height. So first place is over the water body. So here we have the temperature 25 degrees Celsius. Second case, it is over a barren land, and here we have the temperature of the 35 degrees Celsius. And third case, we are considering over the concrete where the temperature of the air is 40 degrees Celsius. Now, if we want to calculate the lapse rate in all the three cases, जहाँ पे 1000 मीटर पे हमारा टेम्परेचर 18.5 डिग्री सेल्सियस है, बट जो ग्राउंड है यहाँ पे हमारा डिफरेंट टेम्परेचर है. सो लैप्स रेट इज डिफरेंस इन टेम्परेचर divided by difference in altitude. So in the first case, what is the difference in temperature? So this is 25 minus 18.5. So this is 6.5 degrees Celsius. So in the first case, it is 6.5 degrees Celsius per kilometer. Now in the second case, अगर हम same altitude difference के लिए lapse rate calculate करें, so here we have the temperature 35 and here we have 18.5. So what is the difference? It is 16.5 degrees Celsius. So for this blue line, lapse rate is 16.5 degrees Celsius per kilometer. And for this green one, that is the third case, here we have the surface temperature of air, that is 40 degrees Celsius, and at 1000 meter we are having 18.5. So if we calculate the difference of this temperature change, so 40 minus 18.5, here we have 21.5 degrees Celsius. So for this, lapse rate is 21.5 degrees Celsius per kilometer. Here we saw that this environmental lapse rate may vary from place to place, and this is also affected by the fluctuation in the weather as well as season, because if any of these changes, the temperature of the earth surface will change, and accordingly the temperature of the air near to the earth surface will change. So this environmental lapse rate is the rate of change in the actual temperature of the atmosphere with height as determined from the observation made by the radiosondes and the aircraft. And this is mainly for the static atmosphere जहाँ पे हम vertical movement को consider नहीं कर रहे. But when we are considering the vertical movement of the air parcel, there comes the concept of the adiabatic lapse rate. So, this adiabatic temperature changes are the changes in temperature that a parcel of air experiences due to the pressure changes as it moves vertically through the atmosphere. Now, this vertical movement of the air parcel, it may be because of many factors, one of which we commonly know that is the convective lifting, where the warm air rises and cool air replaces. But apart from this convective lifting, we also have the frontal wedging, convergence, and orographic lifting that are responsible for rising an air parcel up in the altitude. So, we will discuss these in detail in the next video. Now, we will understand about the adiabatic temperature change. Here, we imagine a volume of air enclosed in a thin balloon like bubble. And in meteorology, meteorologists call this imaginary volume of air as an air parcel. To understand the adiabatic process, let us assume that this parcel is of few hundred cubic meters in volume and it acts independently of the surrounding air and no heat is transferred into or out of the parcel. So these are the assumption on which we are going to understand the adiabatic temperature change. These assumptions are very idealized conditions, but over the short time spans, a parcel of air it behaves much like an actual volume of air moving up or down in the atmosphere. At the lower height or at the lower altitude, there is high atmospheric pressure, but at the high altitude, there is low atmospheric pressure. As we can see, that pressure at the sea level is approximately 1013 hectopascal, while at the height of 5 kilometer, it is only about 500 hectopascal. So, when an air parcel is near to the earth surface, it is subjected to very high pressure, means this air parcel is compressed by the weight of all the air above it. But as this parcel rises, there is less air above it, so the external pressure acting on it decreases. Atmospheric pressure it depends on the weight of air in the column above unit area. In this image, two heights are considered. For this particular height, all these molecules contribute to the pressure, while for this height, only these molecules contribute to the pressure. As we move up in the altitude, as the air density decreases, atmospheric pressure also decreases. And according to the gas laws, if the external pressure decreases, the parcel it expands to maintain the equilibrium. This expansion it results in the increase in the volume of the air parcel and it decreases the density of the parcel because the same number of air molecules now they are occupying a larger volume. Expansion it requires work and the air parcel uses its internal energy for this work and as a result the temperature decreases. So these temperature changes which are due to increase or decrease in pressure and in which heat energy is neither added nor subtracted, these are called adiabatic temperature changes. So these are the result from the changes in the pressure rather than the changes in the heat energy. So when air is compressed, it warms, and when air is allowed to expand, it cools. When any air parcel moves upward, it passes through the regions of successively lower pressure because near to the earth surface we have the higher air pressure while up in the altitude we have the lower air pressure. So as a result, the ascending air parcel means the air parcel which is rising above, it expands and it cools adiabatically. And opposite happens when the air descends downward. So this sinking air parcel or the descending air parcel, it passes through the regions of successively higher pressure and it is compressed and it become warm. So if this air parcel is unsaturated, it cools at a constant rate of 10 degrees Celsius for every 1000 मीटर of ascent. जैसा हम यहाँ पे देख सकते हैं, at the ground surface it is 32 degrees Celsius, but at the height of 1000 meter it is 22 degrees Celsius. At the height of 2000 meter, 22 minus 10, 12 degrees Celsius. फ्रॉम 2000 टू 3000 अगेन 1 किलोमीटर जो हमारा इंक्रीज इन हाइट हो रहा है, 12 माइनस 10, 2 डिग्री सेल्सियस. सो unsaturated air, it cools at a constant rate of 10 degrees Celsius for every 1000 meter of ascent. And opposite happens when it moves downward, it warms or it gets heated 10 degrees Celsius for every 1000 meter of descent. तो यहाँ पे 2 डिग्री सेल्सियस से 12 डिग्री सेल्सियस, 12 plus 10, 22 डिग्री सेल्सियस, 22 plus 10, 32 डिग्री सेल्सियस. So the rising air parcel, it expands and cool at a constant rate of 10 degrees Celsius per 1000 meter, while the sinking air parcel is compressed and warms by 10 degrees Celsius per kilometer. So this rate of cooling or heating, it applies only to the unsaturated air and it is referred as the dry adiabatic rate. Dry because the air is unsaturated. At most of the places on the internet, you will also find the value of the dry adiabatic lapse rate equals to 9.8 degrees Celsius per kilometer. So both are correct, 9.8 degrees Celsius per kilometer or 10 degrees Celsius per kilometer. If an air parcel rises high enough, it will eventually cool to its dew point, means the temperature at which water vapor begins to condense, and it starts the process of condensation in this air parcel. So this altitude at which a parcel reaches the saturation and cloud formation begins, it is referred as the lifting condensation level. And at this particular height, or at the lifting condensation level, an important change occurs. The latent heat that was absorbed by the water vapor when it evaporated is released in this air parcel as condensation takes place. After this height or after lifting condensation level, as this parcel rises above, the parcel will continue to cool adiabatically, but the release of latent heat within this parcel, it slows the rate of cooling. So when this air parcel ascends above the lifting condensation level, the rate at which it cools is reduced. Here we can see it is mentioned 6 degrees Celsius per 1000 meter. So this slower rate of cooling, it is referred as the wet adiabatic lapse rate, and it is also known as the moist or the saturated adiabatic lapse rate. And the amount of latent heat released in this parcel, it depends on the quantity of the moisture present in the air, which is generally between 0 to 4%. Therefore, the wet adiabatic lapse rate, it varies from 5 degrees Celsius per 1000 meters for the air which is having the high moisture content to 9 degrees Celsius per 1000 meter for the air which is having the low moisture content. Here we have the explanation for both dry adiabatic lapse rate as well as wet adiabatic lapse rate. So as the air parcel rises, it expands and cools at the dry adiabatic lapse rate of 10 degrees Celsius per 1000 meter until the air reaches the dew point or the saturation point. So in this example, dew point is considered as the 2 degrees Celsius. At this temperature, the air parcel becomes saturated and condensation begins in this parcel. And the height at which the condensation process starts taking place in this air parcel is referred as the lifting condensation level, and in this example it is 3000 meter. After the lifting condensation level or this height, as the air parcel continues to rise, the latent heat released in this parcel by the condensation, it reduces the cooling. So here it is mentioned that wet adiabatic rate the temperature of rising air drops at 5 degrees Celsius per 1000 meter. So यहाँ पे जो wet adiabatic lapse rate है, that is 5 degrees Celsius per 1000 meter. So this wet adiabatic lapse rate is always less than the dry adiabatic lapse rate, because the latent heat released during condensation, it slows the rate of cooling after the lifting condensation level. Here is the comparison of the temperature difference for a dry air parcel and for a moist air parcel. At the ground surface, both the parcel initial temperature is 10 degrees Celsius. When this air parcel rises, initially both will cool at the dry adiabatic lapse rate of 10 degrees Celsius per 1000 meter, and at the height of 1000 meter, these both parcels are having the temperature of 0 degrees Celsius. After this height, the dry air parcel, it continues to cool at the dry adiabatic lapse rate only, because it is not having any moisture content. So at the height of 2000 meter, इसका temperature है minus 10 degree Celsius, and at the height of 3000 meter, इसका temperature हो गया minus 20 degree Celsius. यहाँ पर ये diagonally show कर रहा है, but this is only the representation of air parcel at different altitude and having different temperature. Here we are considering the air parcel which is moving vertically upside. Now let us see another air parcel, that is the moist air parcel. So at this particular height, water vapor begins to condense. अब जब condensation होगा, latent heat will be released in this air parcel, which will decrease the rate of cooling. So now we can see the wet adiabatic lapse rate is 6 degrees Celsius per kilometer. So at the height of 2000 meter, here the temperature of this moist parcel is minus 6 degrees Celsius. And when it is further moving upside, so at the height of 3000 meter, it is having the temperature of minus 12 degrees Celsius. So if we compare these two air parcel at different altitude, dry air parcel is much cooler in comparison to the moist air parcel. So by now we know that lapse rate is of two types, environmental lapse rate and adiabatic lapse rate. Environmental lapse rate is the rate of change of temperature in the troposphere, and here we consider static environment, and the value is average of 6.5 degrees Celsius per 1000 meters. And the other one is the adiabatic lapse rate, where we consider the vertical movement of the air parcel and the temperature change of the air parcel due to pressure changes. It is referred as the adiabatic lapse rate, and it is of two type, dry adiabatic lapse rate when we are considering the unsaturated air parcel and the value is 10 degrees Celsius per 1000 meter, and the other type is the wet or the moist adiabatic lapse rate, which is also known as the saturated adiabatic lapse rate. This is for the saturated air parcel, where the latent heat released during condensation slows the rate of cooling process, and the value of the moist or wet adiabatic lapse rate is 5 degrees Celsius to 9 degrees Celsius per 1000 meter, depending upon the moisture content in the air parcel. With respect to the adiabatic lapse rate, the atmospheric condition can be defined as the subadiabatic or superadiabatic. Here we are considering 2 points on the y-axis for which temperature can be defined on this particular axis. अब यहाँ पे कोई भी demarcation नहीं है, so we are considering the width as the temperature change. So now for subadiabatic condition, for the same elevation, if we see, this is the temperature width that represent that the rate of change for this much elevation is much less than the adiabatic lapse rate. And for the superadiabatic condition, we can see that the rate of change for this lapse rate is much higher than the adiabatic lapse rate. So superadiabatic means more than the adiabatic lapse rate, and subadiabatic means less than the adiabatic lapse rate. And here we have this inversion condition, which is showing the increase in the temperature with height. These lapse rate are very important because the difference between the environmental lapse rate and dry or moist adiabatic lapse rate, it determines the vertical stability of the atmosphere that defines the tendency of an air parcel to return to its original position or to accelerate away from its original position. In this video, we came across these topics: processes that lift air, inversion, and the atmospheric stability. So, our next videos will be on the same topics and we will cover each of them in detail. Majority of the content of this video have been taken from the chapter Moisture and Atmospheric Stability in this book, that is the Atmosphere and Introduction to Meteorology, and some of the content have been taken from this particular website. We will meet soon in the next videos. Thank you and best wishes.